This is AP Calculus ABB, Unit 2, Definite Integral, Lesson 4, Definite Integrals and Antiderivatives, the second installment. There's 4 objectives in this lesson, and that's a bit much to squeeze into one 10-minute video. So I'm going to attempt to do the remaining 2 objectives here. And I've decided to present the last one first because I think the order works better that way. And that's this. Consider this definite integral, the integral from a to b, or from a to x, the integral from a to x of f of x dx. And consider that that integral is some function capital F of x. So capital F of x represents the integral that is the integral of the function lowercase f of x. Okay, some function of x turns into some other function of x. It's really that simple. Okay, and let's consider this. Let's substitute let x equal a. Right, substitute a. Then we get the integral from a to a of f of x dx equals f of a, capital F, and we just replaced x with a, and we get f of a, right? Plus some constant c, okay? Plus some constant c. Oh, and I forgot to place that in the original one. Plus some constant c. We need the constant of integration, okay? Well, what is the integral from a to a? Let's consider that for a moment. We have some function f of x, and we're finding the area under the curve from A to A. Well, we're talking about a rectangle with 0 width. It doesn't matter how tall it is. 0 times anything is 0. So this integral is 0. Well, let's solve this for c. We can see, hopefully, that c is negative f of a. Right? c is negative f of a. Okay, now let's rewrite the original expression. The original expression is the integral from a to x of f of x dx equals f of x plus negative f of a, or minus f of a. Okay, so that c has to do with the f of a. And let's do this. Let's let x equal b. In that case, then, we get the integral from a to b of f of x dx is f of b, capital F of b, minus capital F of a. Okay, and this result here is a formula. It's actually a result of something called the fundamental theorem of calculus. It says that to find a definite integral, find the integral with b inserted, with the upper boundary, minus the integral with the lower boundary inserted. Let me give you an example. So let's say I want to find the integral from 2 to 5 of x squared plus 7x minus 4 dx. Okay? Then I'm going to find the indefinite integral. So x squared becomes x cubed over 3. X becomes x squared over 2, so plus 7. Let's do 7x squared over 2 minus 4x. Okay? And we're going to now, and then here's the notation we use. We use a straight line, and we indicate the lower bound and upper bound from 2 to 5. And here's how this looks. We insert 5, f of b, so 5 cubed over 3 plus 7 times 5 squared over 2 minus 4 times 5 minus, now we're going to insert 2 cubed over 3 plus 7 times 2 squared over 2 minus 4 times 2. Okay? And the rest is arithmetic. Lovely. 125 over 3. 25 times 7 is 175 over 2. Minus 4 times 5 is 20. minus, change all the signs. Okay, so minus 2 cubed is 8 over 3. 2 squared is 4. 4 divided by 2 is 2. 2 times 7 is 14. Plus 8. Okay, and boy, there I finished this. I'm going to leave it as is for now and let you finish the arithmetic if you want. Okay, but you get the idea. To find the definite integral, we find the indefinite integral without the constant c, and we subtract. So in fact, if you wanted, you could think of c being there, but c would be the same for both integrals. And then when you insert it, the c's would subtract or subtract out. And it essentially comes out to the same argument as before. Okay, that brings us to the second objective, and that was finding the average value. Okay, and we're doing good on time here. So, average value. If you want to find the average of a list of numbers, the way to do that is to sum them all up. Sum of the x sub I is divided by n, right? Sum of each term of the series added up and divided by n. Well, we've just demonstrated that an integral is a sum of a bunch of slices. It is a sum. So if I want to think of the integral from a to b of f of x dx as the sum, then all I need to do is divide by the width of all the slices put together, or the divide by b minus a, which is the range. And that is the formula for the average. The average f value, the average value of a function between a and b, is 1 divided by b minus a times the integral from a to b of f of x dx. Okay, so let's take a simple example here, and let's say f of x equals x squared minus 5. Okay, we'll keep it simple, hopefully. All right, and let's find the average value. Let's find the average, f average, from 2 to 5. Okay, that would be 1 over 2 minus 5. Okay, 1 over 2 minus 5 times the integral from 2 to 5 of x squared minus 5 dx. Okay, let's evaluate that here. So we get equals 1 over negative 3, or negative 1/3, times the integral of x squared is x cubed over 3 minus 5x from 2 to 5. Okay, so let's see, negative 1/3 times 5 cubed over 3 minus 5 times 5 minus, insert 2. 2 cubed over 3 minus 5 times 2. Okay, and the rest is arithmetic. Let's go ahead and work this one out here. Okay, 5 cubed is 125 over 3. 5 times 5 is 25. Distribute the negative, change all the signs. So minus 8/3 plus 4. Okay. And equals negative 1/3 times 125/3 minus 8/3 is 117/3 minus 21. 117 divided by 3 goes evenly. So let's go ahead and distribute the, we won't distribute yet. But 117 divided by 3 goes 3, 9, 2, 27, 39 minus 21. 39 minus 21 is 18. 18 divided by 3 is 6, so negative 6. Okay, so the average value of f between 2 and 5 is negative 6. Okay, and that's an interesting result. Now that introduces us to something called the mean value theorem for integrals. Okay, And here's what the mean value theorem for integrals says. All right, it says that if you have some function defined between a and b, so a and b, okay, some function f of x defined between a and b, and the average is L, okay, and the average value is L, then it would say there exists, here's the symbol for there exists, a C on AB, so a C between A and B. It's got to be in the domain between A and B, such that f of C equals L. Okay. In other words, there is a C, there is a value between A and B, C, such that if I put in C, I'll get out the average value. Okay, and that's the mean value theorem, MVT, for integrals. Okay, mean value theorem for integrals says that if I find the average value, then there is some value on the domain between A and B, between the boundaries, where the function gives me that value, gives me that average value. All right? And so you might be asked, find the value C guaranteed by the fundamental theorem of calculus, in which case we would do this. We would say, well, this is -6, right? But what did we say? Where the integral, where the function value is -6. The function, the original function, is x squared minus 5. So where does x squared minus 5 equal 6? Because that's f of x, right? Okay, so let's figure that out. Add 5, x squared is 11. And x is the square root of 11. Now we have a positive or a negative 11. And if I were to graph this in Desmos, okay. If I were to graph x squared minus 5, okay, from what did we say, 2 to 5. Okay, so here's the function graph right here. Okay, and we have the mean value, or the average value, which is y equals 6, right? That's the average value. And where does that happen? Well, it happens at square root 11. X equals square root. Let's see if this works. Drum roll, please. There it is. That happens to be right where the average meets. The square root of 11, 3.317. Okay. All right. So we've verified that there is a value C, 3.317, where the output of the function is the average value. All right, so I think that covers the basic material. And take your time. If you need any help, feel free to book a live lesson. I hope to work with you more soon.